Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures on computer networks. We will be looking at the network layer today. With respect to the network layer, we will be looking at routing algorithms and protocols. So, we have already talked about one routing algorithm called the distance vector routing. So, we will take a look at that again, and we look at the protocol, the RIP protocol, which is associated with, which uses this distance vector routing. We will also take a look at the link state routing protocol and the OSPF and the associated OSPF protocol. So, these two routing algorithms which are used in the internet today are distributed routing algorithms, which are very popular algorithms. This distance vector routing and link state routing algorithm. As I said, distance vector routing is used in the RIP protocol and link state routing is used in the OSPF protocol. In both these algorithms, the network is basically represented as a graph. That is, the nodes are connected by networks. Network can be a link or a LAN. The network interface has a cost. The networks are destinations, and net v comma w is an IP address of a network. So, this is typically what we do to represent it as a graph. So, you take a look at this picture here. So, I have v connected to w through this net v comma w. For ease of notation, we often replace the clouds, which is actually the network, between the nodes by simple links. Okay, so we could just connect this up as a single link with a cost v comma w, which indicates that there is a cost between the nodes v and w. So, if you look at the distance vector routing algorithm, the routing table basically has this information of destination via which hop, which next hop does it go through, and what is the cost to that particular destination. So, for instance, net here, if this is the destination, so you have an entry here which says net, and you go through the node n, so via the next hop is n, and the distance that you have is v comma net. Okay, the distance that you have from v to net, that distance value is stored here as the cost. So, you can see here C of v comma w is the cost to transmit on the interface to network net v comma w. Net v comma w, whatever we are showing here, is the network address of the network between v and w. Again, the network can be a link, but it could also be a LAN. If you look at the messages that are used in the distance vector routing algorithm, so we just saw what the routing table looks like. The nodes now send messages to their neighbors which contain routing table entries. So, a message has the format net comma d of v comma net, which means my cost to go to net is d of v comma net. D is the distance or the cost to go from to that particular network. So, v to net to n. Okay, so this is what you have as the information that is sent in as messages which are exchanged in the distance vector routing algorithm between the various nodes. So, when do we actually send this information? So, you have this routing table at a particular node. So, you can see that at every node you have the destination to the various networks that you have net 1 to n, the different hops through which it is sent, the corresponding distance. So, this information of this destination and the cost, not the via information, but the destination and the cost is what is sent as an update periodically to its neighbors. So, periodically we say each node sends the content of its routing table to its neighbor, right. So, if you have these nodes m, v, w and n, they keep sending this information periodically amongst each other. So, this periodic updates are sent at the end of a certain time period, typical value is about 90 seconds. You also have what are called triggered updates, that is, if a metric changes on a link, a router immediately sends out an update without waiting for the end of an update period. So, you have both triggered updates and we have periodic updates. Now, when you have a full routing table update, most distance vector routing protocols send their neighbors the entire routing table, not just entries which will change. Now, you could have these again are possibilities that we have, just as we talk about triggered update and periodic update as two options which are used. Similarly, we could have a full routing table update or you could have a partial routing table update, but most of the distance vector routing table routing protocols normally send the full routing table. Another feature that is used normally is route invalidation timers, that is, when the routing table entries are invalid, you will have to remove them from the table. So, how do you find out if they are invalid? If they are not refreshed, then the routing table entries become invalid. So, how do we do that? We have a value which is associated with every entry. A typical value is to invalidate an entry if no update is received after 3 to 6 update periods. So, So, you kind of wait for about 3 to 6 update periods. If you do not get any updates about a particular routing table entry, you remove that from the routing table. So, you consider that it is stale and it is not been refreshed, so you can remove it. Now, this obviously will work only if we are using full routing table updates, because only when full routing table updates are used, you can wait for 3 to 6 update periods, check if a particular routing table information has been received or not. If it has not been received, you can remove that entry from the routing table. Now, coming to the RIP protocol, which implements this particular routing algorithm. Now, RIP is a very straightforward implementation of the distance vector routing algorithm. Now, it is a simple intra-domain protocol, that is to say that it is used within an autonomous system. Now, each router advertises its distance vector every 30 seconds or whenever its routing table changes to all of its neighbors. That is the way it is implemented in the RIP protocol. Now, RIP always uses 1 as link metric, and maximum hop count is treated as 15 with 16 equal to infinity. Routes are timed out, that is set to 16 after 3 minutes if they are not updated. A little bit on the RIP history, on the RIP history, the RIP protocol history. 1988 was when the first version of RIP was floated. So, this was floated in RFC 1058. In 93 you had RIP version 2, which added provision for subnet masks which could be used with each route entry, and also allowed for classless routing. Now, we will understand what we mean by classless and classful routing when we take a look at the IP layer protocol in detail. But just remember that you have version 1, which was kind of a primitive version, and version 2 took care of some of the advances that took place in the IP field. So, the 1998 is when the current version of RIP v2 was introduced, and that has been the one that has pretty much been used. So, if you look at the RIP version 2 packet format, now the RIP message itself is carried as a UDP packet. So, it is carried within a UDP packet. So, you have a UDP header which is followed by the RIP message. If you look at the RIP message, it has a command field, a version field, then there are some bits which are set to all zeros, an address family again on all zeros, you have a 32-bit address, and then you have the metric field, and then up to 24 more routes which can be supported on this. You can see that the entry that you have basically this whole thing from here to here is one route entry. That is, you have the address of a particular destination and the metric, the cost to that particular destination. This is what you have for every route that needs to be sent, and you can have 24 more such routes which are advertised in a single RIP message. Okay. So, we say one RIP message can have up to 25 route entries. So, this command field here identifies whether it is a request message or whether it is a response. The version here will indicate what version it is 2 in the case of RIP version 2. The address family here indicates whether it is the IP addressing family which is used, or whether it is whether it requests a full routing table. Now, what we do, I mean the 000 here indicates that we are requesting full routing table. Now, 2 for IP basically indicates that the RIP protocol can be used not only for IP, but for any other networking protocol as well. So, for IP the address family here is given as 2, and correspondingly these bits over here, these fields that we have here, they are used for the IP address, and since IP address is only 32 bits, we use just one 32-bit address over here, the rest are unused. These would be set to all zeros, but if you had some other routing protocol that was used, then you would have, and if they needed a larger number of addresses, these bits would be used to specify those addresses. So, this is the 32-bit address is the address of the destination, and this cost here is the cost measured in hops, and as we just said, RIP measures it in terms of number of hops. Right. Coming back to the other information that you have, so you could have route tags which are specified over here, that is RIP version 2 I said allows you to support subnet masks and so on. So, then we have route tags used to carry information from other routing protocols, which for example, this could have information such as the autonomous system number. Then subnet masks for you, if they are used, they are specified here, and identifying a better next hop address on the same subnet than the advertising router. So, that is the next hop IP address, this could also be specified. So, these values which were zeros in one version of the RIP now have provision for specifying subnet masks and next hop IP address. So, you have additional information that can be specified, but you can see that the message format pretty much remains the same, it is just some fields which are used differently. So, if we look at routing with RIP, you have initialization which basically says you send a request packet, the command field is equal to 1, address family of all zeros and all interfaces. RIP version 1 uses broadcast if possible, RIP version 2 uses multicast address if possible, and for requesting the routing tables from neighboring routers. Then when a request is received, routers that receive the above request send their entire routing table. When a response is received, you update the routing table, and then regular routing table updates are sent every 30 seconds. That is, you send all or part of the routing table to every neighbor in the response message. Triggered updates are sent whenever the metric for a route changes, then you send the entire routing table. So that is what we have in the RIP protocol. Now we move to the link state routing protocol. The strategy in a link state routing protocol is that you send information to all nodes, not just the neighbors. So you send to all nodes information about the directly connected links, and we do not send the entire routing table. You can see that this is the major difference that you have between the distance vector routing protocol and the link state routing protocol. So here what we do is we send information to all nodes, not just neighbors, but you send information about the directly connected links, not the entire routing table. You can see that just the reverse of what happens in the distance vector routing. In distance vector routing, you are sending information to your neighbors about all the other nodes that you are connected to, about the entire routing table that you have. Here it is the other way around. So each node then constructs the graph of the entire network and computes the least cost path to any destination. So let us look at how that will happen. So if I have so many different nodes here, A, B, C and so on, right. So what happens in this link state routing is every node sends information about neighbors to every router. So A would say that it is connected to B, F and E with a particular cost, and this information would be sent to all the other routers. So similarly, every router would look at which are the neighbors to which it is connected and send that information to all the other routers. So now let us look at how exactly this information is consolidated. So each node requires the complete topology information. So the link state information is flooded to all the nodes, because we said it has to be sent to all the nodes, it has to be flooded to all the nodes. And what is very important here is that this link state routing has to be guaranteed to converge, and it is guaranteed to converge. That is, when all the flooding information is finally obtained, when all the information about all the nodes is finally obtained, and you construct a graph, they will all converge to the same value when you compute the shortest path from any node to any other node on this graph. Okay, these are the basic properties that we have of this link state routing protocol. Now this guarantee to converge within a reasonable amount of time is one of the major advantages of the link state routing protocol, and that is where it significantly differs from the distance vector routing protocol. Now we have seen in an earlier lecture with respect to distance vector routing protocol that you have problems of convergence, you have problems like the count infinity problem, and that is something which is taken care of in the link state routing protocol. The count infinity kind of problems do not occur here because you have a guaranteed convergence, and this happens because you have the complete topology information which is available. We will take a short break now and come back and look at the details of the link state routing protocol. Welcome back after the break. We have been talking about the link state routing protocol and how it differs from the distance vector routing protocol. So in link state vector protocol, as we said, each node sends the information about its connectivity to its neighbors to all the other nodes in the network, and each node now will construct a complete graph of the network. So let us look at how this happens. So the basic principles that we have in link state routing are as follows. So each router, as I said, establishes a relationship with its neighbors, that is, it finds out who are its neighbors. Adjacency with its neighbors is what it finds out. Then each router generates what are called as link state advertisements or LSAs, which are distributed to all routers. So what does this LSA normally consist of? It consists of a link ID, state of the link, cost and neighbors of the link. So this information is what is sent in this LSA packet. So each router now maintains a database of all the received LSAs, that is LSAs received from each of the other nodes which are there in the entire network. So that is, you have a topological database or what is called as the link state database. Now this describes the network as a graph with weighted edges. Each router uses its link state database to run the shortest path algorithm. Now typically the shortest path algorithm that is used is the Dijkstra's algorithm to produce the shortest path to each network. Now remember that all of them will have the same link state database eventually, and they will run the same algorithm, therefore they will end up with the same path to go from any source to any destination. So the consistency that you have in the network is definitely maintained. So the link state pack will look like this. You have the advertiser which says the link state's ID followed by network, cost and the neighbor. Okay, this is what the link state packet would look like. And we said the link state packet is sent to all the other neighbors by means of what is called as reliable flooding. Now what do we mean by reliable flooding? You store the most recent LSP from each node and you forward the LSP to all the nodes but one that sent it. You generate the new LSP periodically. So to distinguish an older LSP from a newer LSP, we use something called a sequence number, and the sequence number is incremented. So you start the sequence number at 0 when you reboot, and we also have a TTL field, a time to live field which is used. You decrement the TTL of each stored LSP. So now look at what is happening here. Now you store the most recent LSP from each node. So this is what we are trying to basically achieve here is reliable flooding. Now what do we mean by reliable flooding? You are flooding the entire network with these LSP packets. So we want to make sure that this is not just a flooding of LSP packets alone which takes place in the network, but after a point of time this flooding of LSPs will kind of stop, it will kind of converge. Now which means I should not have LSP packets going back and forth in the network continuously, which is why we make use of all these different techniques. We use a sequence number to identify when a new LSP packet is being sent, so that the old one can be discarded and the new one can be retained. We use this TTL field in order to make sure that when you have loops which are there in the network, you do not have packets being sent over and over again in the loop. That is, once the TTL goes to 0, you will drop the packet. Similarly, you forward the LSP only on all nodes except the one that sent it. So which again helps you to reduce the amount of flooding that actually takes place and when the TTL goes to 0, you will discard the packet. So if you look at the basic operation of the link state routing protocol in the at each node, so each node receives LSAs, stores them in the link state database and forwards the LSAs on other interface, so that LSA flooding takes place on other interfaces. Using this link state database, it runs the Dijkstra's algorithm and constructs its IP routing table. So this is the overall operation of the link state routing protocol as it can be seen in each router. Now coming to the Dijkstra's shortest path algorithm for a graph. So what we do here is you have a graph n comma e with n as a set of nodes and e is the set of edges. Now dv comma w is the link cost. Now dv comma w is set to infinity if v comma w does not belong to your e, the set of edges, and s is the source node. Given this input, let us look at what happens. The output basically is dn, which is the cost of the least cost path from node s to node n. From s to n is what we want to find out. So you have an algorithm which essentially identifies the least cost path and arrives at the final route that is to be taken from the node to a destination. I will not go into the details of this. You can this is the normal shortest path algorithm that you would have been exposed to, that you had already studied in your course on data structures and so on. So so this is the Dijkstra's algorithm that is used, a very well known algorithm, and the same algorithm being run on all nodes makes sure that you have a consistent path information that is obtained. Now coming to the OSPF protocol, which actually uses this link state routing algorithm. OSPF stands for Open Shortest Path First. Now this is the most important link state routing protocol on the internet. Of course the RIP protocol is also used, but OSPF is kind of used whenever we are looking for proper convergence of the information. The complexity of the OSPF, as we can see, is significant, and we will take a look at some of those details. Now if you look at the features of OSPF, now OSPF provides authentication of the routing messages. Secondly, it enables load balancing by allowing traffic to be split evenly across routes with equal cost. Now these are some additional features that OSPF provides over and above what is normally provided by the link state algorithm. Now when we say provides authentication of routing messages, that is very important, because you can have malicious routers just sending wrong information, and that information could be flooded among all the routers, and if that wrong information is flooded, you would end up with totally wrong picture of the network, and that would completely destroy the entire routing table that you are constructing. So, some amount of authentication is provided for, and OSPF provides for authentication of its routing messages, so that you know that you are getting authentic information from a router and you are getting authentic information from an authentic person. Secondly, allowing of load balancing. This is something which is again a good feature of OSPF. So, if you have two routes with equal cost, you could use both the routes alternatively, so that you can kind of balance the load on both these routes. Third, it allows for type of service routing to set up different routes depending on the TOS field. That is, you can have different metrics that you could use. Now, we saw that in the RIP protocol, only the cost, that is the link, the hop count is what is used as the metric. Every link is just given a cost of 1, whereas OSPF allows you to have different costs allocated, different costs used depending on what type of service you want to have. For instance, you could have different link metrics. One could be based on the bandwidth, one could be based on the hop count. There are various, one could be based on reliability. So, you could have different types of service specified, and based on the type of service you could choose different routes. So, this is one of the major advantages of OSPF. Fourthly, it supports subnetting. Now, subnetting is also supported by RIP, but it is supported on OSPF as well, and it supports multicasting as well, and it allows for some hierarchical routing. Now, what actually OSPF does is, within a domain, the network can also be divided into what are called as areas, and this within an area you have the information which is aggregated, and the aggregated information can be sent to other areas. So, and this actually helps to the network to scale. The amount of information that needs to be exchanged is kind of reduced because of this kind of a feature. So, let us look at an example network. So, let us say I have these different routers here. Okay, so 10.10.10.1, 2, 3, 4, 5, 6, whatever. Okay, I have these different routers. The router IDs are selected independent of the interface addresses. Okay, now you have one address over here and one address over here that you can see. So, the router ID is normally what is done is you either choose independent of interface address, or you choose one of the least address as the ID of the router. Now, link costs are called metric. Now, the reason we call it as metric is that as we just said, you could use different types of metrics, right. It could be reliability based, or it could be cost based, bandwidth based, whatever. And metric is normally in the range of 0 to 2 power 16, and metric can be asymmetric. That is, in one direction I could have a different metric, in other direction I could have a different metric. So, all these are possible. So, when you have a link state advertisement that is sent, this is typically what it would look like. The LSA of a router 10.10.1 10.10.10.1 would be as follows. So, the link state ID, it would say 10.10.10.1 is the router ID, and the advertising router, okay, the route that again is the same as the router ID 10.10.10.1. Number of links, okay, see 3, that is 2 links plus the router itself. Okay. So, it will say that there are 2 links over here plus the router itself. So, number of links is given as 3, and then you have the this information being sent as the link state advertisement. So, each router sends its LSA to all the routers in the network, as we saw using a method called reliable flooding. Now, the link state, so description of link 1, you will have description for each of the links also in that link state advertisement. So, link ID 10.1.1.1 and the metric associated with it. So, the description of link 2, link ID 10.1.2.1, metric 3. Link ID 10.10.1, now remember this is the node itself, right. So, the metric is 0. So, this is the information that would be sent in the link state advertisement. So, now when this link state advertisement is sent, each router has a database which contains the LSAs from all the other routers. So, that is maintained at each of the routers. So, the database would look like this. You will have the LS type, link state ID, advertising router, checksum, LS sequence number, LS age. LS age is the same as our TTL that we talked about. So, this is the information that will be maintained at each of the nodes as a database. So, now if we look at this database, the collection of all LSAs, as we said, is called as a link state database. Now, each router has identical link state database, so which is useful for debugging because each router has a complete description of the network. And if neighboring routers discover each other for the first time, they will exchange their link state databases. So, this again helps to make the convergence faster, or rather to make the latency less. The link state databases then are synchronized using reliable flooding. So, this is the overall mechanism. So, coming to the OSPF packet format. So, again you have the OSPF message, which consists of a header and the body. The OSPF packets, remember, now there is a difference over here. The OSPF packets are not carried as UDP payload. OSPF is carried directly as an IP packet. So, OSPF has its own IP protocol number, which is 89. That is IP header, and then following that the message, the OSPF message directly is carried as the as an IP packet. Now, the TTL is set to 1 in most cases. The destination IP would be the neighbor's IP address, or it would be 224.0.0.5 or 224.0.0.6. That is all OSPF routers or all the D routers. So, these are multicast addresses which are used to indicate that you are sending it to some of these to these different routers. Okay. Now, coming to the OSPF message as such, you have the message header followed by the body of the OSPF message. The body of OSPF message consists of message type, what specific data is being carried, followed by LSAs. Now, link state advertisement again will have an LSA header and LSA data, right. So, this is what the OSPF message. So, if you look at the OSPF message header, it consists of a version, type field, message length, source router IP address, area ID, a checksum, authentication type followed by authentication information. Remember that we just said that OSPF supports authentication. So, the type of authentication is specified in this particular field, and the information for authentication. For instance, if you are using a password based authentication, authentication type field here would indicate that you are using a password based authentication, and the actual password would be carried in this authentication field. Now, version, type, message length, all these are quite self-explanatory. Checksum is again a typical 16-bit checksum that is used in most of the IP related protocols. Okay. So, the version field here is version, the current version is 2, so it will show that it is 2. The type here will identify whether it is a hello message, a database description message, a link state request message, a link state update message, or a link state acknowledgement message. So, that is indicated by the type field. The area ID here is the ID of the area from which this packet originated. So, remember I just told you that you could have the entire area in which your OSPF protocol is being run divided into the entire domain being divided into multiple areas. So, in which case you need to give an ID for the area, that is what is specified in this area ID field. Checksum, as I said, is the standard IP checksum, and authentication type here will indicate that you are coming to the what kind of authentication is being specified. Coming to the LSA format, the OSPF LSA format, you have the link age, link type, link state ID, advertising router, link sequence number, checksum length, followed by information about each link, link ID, link data, link type, TOS metrics and the metric as such. So, you have the complete information being specified over here. Now, discovery of neighbors is done by means of the OSPF hello packets, and if two routers share a link, they can become neighbors and establish an adjacency. After becoming a neighbor, as we said, the routers exchange their link state databases. So, this is something that we have already talked about. Dissemination of LSA updates take place, that is through by means of these LSA update messages, and there are certain exceptions of course. Infrequently, about every 30 minutes a router will flood LSAs even if there are no new changes. Normally it is sent only when you have changes, but you also send it in certain exceptional cases. Okay. And acknowledgements of LSA updates happens through an explicit tag or implicitly via reception of an LSA update message. So, this is basically how the OSPF protocol works using all these LSA messages. So, to summarize, what we have looked at today are the basics of two different routing algorithms, the distance vector routing and the link state routing, and the protocols that are associated with these two, which are used currently in the internet, RIP protocol and the OSPF protocol. So, a few questions that can help in terms of assimilating today's content. Question number 1, what is the idea used in distance vector routing? Question number 2, what is the disadvantage of the distance vector routing algorithm? Question number 3, what is the idea used in link state routing? Question number 4, what is meant by reliable flooding? Question number 5, what are the contents of an LSA packet? Question number 6, which algorithms used to calculate the shortest path in OSPF? So, that would be the set of questions that you have. Thank you.